Hello, in this video we solve one exam problem on the topic of Taylor polynomial. The question is, determine the Taylor polynomial of degree 2 around x equals to 1 of this function g of x equals to e to power minus x squared. That would be a good idea if you pause the video at this point and try to solve the problem yourself first. Okay. So here, let me start with the general formula. So the nth order Taylor polynomial around point A is a polynomial which we learned is equal to sigma. K goes from 0 up to that n. The kth order derivative of my function, the name of my function here is g, so I would write it as the kth order of g calculated at point A divided by k factorial, but times x minus a to power k. So in this problem, it is mentioned that the degree is 2, so it means n is indeed 2. And it is mentioned that we are interested to do the calculation around x equals to 1, so this means a is equal to 1. So I go back to my formula, I replace every n here and there with 2, and I replace every a here, here, and here with 1. But because a remains the same, I will suppress this a from here. So I would write p sub 2 of x equals to sigma, k goes from 0 up to n, which in this case is 2, the kth order derivative of g calculated at a, which is 1, divided by k factorial, and then multiplied by x minus a, 1 to power k. So how many terms are involved in this sigma? 3. K equals to 0, one term, k equals to 1, second one, and k equals to 2, the third one. I've always preferred to open it up, okay? So if I put 0 here, I get g of 1. If I put 1 instead of k, so it becomes the first derivative of g at 1 divided by 1 factorial, and then I have x minus 1. And then finally, if I replace k with 2, I will have g double prime of 1 divided by 2 factorial, and then I have x minus 1 to power 2. So now my duty is to calculate these three numbers, and that's it. Calculating g of 1 is straightforward. G of x is given to be e to power minus x squared, so when I want to calculate g of 1, I simply replace x with 1. So it becomes e to power minus 1. But in order to calculate g prime of 1, I have to differentiate my function first. And if I want to differentiate my function, I will use this formula from the chain rule. If I have e to the power of u is a function of x, and my goal is to differentiate that function with respect to x, what I will do, I will copy the function repeats itself, but because of the chain rule, I have to multiply it by the derivative of the exponent, the derivative of u. So here I give the role of u to minus x squared, and I do the calculations according to the formula I just mentioned. So the function repeats itself, but I have to multiply by the derivative of the exponent, so it becomes minus 2x, the derivative of the exponent. I prefer to write it on the left, and I will have e to power minus x squared. Now everything is ready to calculate g prime of 1. So I replace this x and that x with 1, so the answer simply is minus 2e to power minus 1. Okay, for calculating the last number, I have to differentiate this function once more, yes? So this is g prime of x. In order to find g double prime, I have to differentiate this function. But you see, this is the product of two functions, so I have to use the product rule. So the derivative, the second derivative will be the derivative of the first one multiplied by the second one itself. The derivative of the first one will be minus 2e to power minus x squared plus the first one multiplied by the derivative of the second one. But the derivative of the second one is exactly the same function itself, you see? Because this function is just the function g. So when I differentiate it, it becomes minus 2x e to power minus x squared. Yes. So if I simplify this a little bit, so I copy and paste the first term. but minus 2x times minus 2x will be plus 4x squared, and then I have e to power minus x squared. But now my goal is to calculate g double prime of 1. This is my g double prime, so I replace every x with 1. If I do that, I will get minus 2e to power minus 1 from the first one, and plus 4e to power minus 1 from the second one. So 4e to power minus 1 minus 2e to power minus 1 is just simply 2e to power minus 1, and that is finally my last number. Now I go back here, I replace g of 1 with this number, I replace g prime of 1 with this number, and I know that 1 factorial is just 1. And here I replace this one with this number, but because this 2 factorial is also 2, so that 2 will be cancelled. That's it. So the second order Taylor polynomial will be e to power minus 1 plus, minus 2e to power minus 1 times x minus 1, and then finally plus e to power minus 1 x minus 1 to power 2. So usually that's good enough. But here we can simplify this a little bit because that's not a big deal. For example, I can see that e to power minus 1 can be factored out, and I can write it as 1 over e. It's more beautiful. And then there will be 1 left here, minus 2 times this is left. So let me open a pair of brackets, 1. And this minus 2 I multiplied inside, so it becomes minus 2x plus 2. And then when I factor this out, I raise this one to power 2. So it becomes plus x squared minus 2x plus 1. And then one more step. So p2 of x will in principle be 1 over e. So I have 1, 2, and 1, which is 4. Minus 2x is minus 4x. And then finally plus x squared. So this is the final answer, final simplified version of the answer to this problem. That would be a good idea if we also check to see how good this P2, this polynomial, approximates the real function. So let me switch to the application GeoGebra. Okay, so this is in GeoGebra Classic 6. Because I want to do precise algebraic calculations, I switch to cast view, and then here I start typing Taylor. Okay, so this suggests me this syntax. So let me give a little bit of a space here. So here, the first one, if you remember, it was the function. So the function here is exponential. So I use this virtual keyboard to type e to power minus x to power 2. And then if you remember, the next value was the value around which the Taylor polynomial is supposed to be written. In this problem, it was 1. And the degree was 2. And when you press enter, you get this. Of course, if you want to simplify it and see the graph of it, you just click here. Yeah, it is exactly the simplified version of the Taylor polynomial we did by calculation, and this will be your parabola. But if you want to compare it, let me also draw the graph of the original function, which is exponential to the power of minus x to power 2, and then I press enter. If I want to have it here, so I will click on this circle, it will draw it here. So these two graphs, as you see, are the graphs. This curve that you see in the bottom is actually the real curve, and this parabola is the approximated curve. Okay, but immediately you see that when I get close to number 1, our eyes cannot even detect that we have two graphs, because both of them are drawn in green. So you see that when I am in the vicinity of 1, yes, there is no deviation. Of course, might be we zoom more, we will actually finally find some deviations, but it already shows that if I am in the neighborhood of x equals to 1, then instead of working with this a little bit more complicated function, it would be preferable to work with this polynomial function, which is the philosophy behind why we are learning about Taylor polynomials in the first place. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.